Hello there, this is Douglas Rumbaugh, and welcome to the second video in my series on Introduction to C pointers. In this video, we're going to be discussing basic pointer usage with respect to stack variables. So, as a very quick review of what we discussed last time, when you're talking about a C program running on the computer, that program is represented as a process, and that process has its own particular view of memory called a virtual address space. And this is a general roadmap which we have been using for what this virtual address space looks like. At the low addresses, you have text, which is the actual code of the program. And then you have some other stuff, which we will talk about later. And then up in the high addresses, you have the stack, which is where function calls are tracked and the local variables to those functions are stored. In this video, we're going to take a look at a simple motivating example, which is just creating a function which increments a variable. So let's take a look at the code for that first. Hop on over here. If you haven't already, make sure you git pull to update your repository and then check out the branch for episode 2. And we are interested in the increment1 program right now. And what this is, of course, broken. And if you have spent time working with programming and functions before, you'll probably look at this and tell it is broken. We're going to talk about why it's broken and then use pointers to fix it. So that's the game plan for this particular video. Now, the basic idea of what we want to have happen here is we have this variable x, which in main we initialize to 5. And what we would like to do is we would like to call this function to increment it. This syntax in C just does an in-place update, so 5 will become 6. And then we would like for that 6 to be reflected out here in main when the function call returns. Now, we go ahead and compile and run this. You will, as expected, see that it doesn't work. The variable is initialized to 5. When we call increment, the variable updates to 6, but then back in main we have 5 again. So why is it that this is happening? Well, to understand this, we have to take a look at how exactly function calls work in C. That's the first important thing to note. Now, C uses what's called a pass by value convention for calling functions. There's a couple of different ways to do this. You can pass by value, pass by reference, and there are some strange languages that use something called pass by name. We're not going to talk about those other two because they don't even exist in C. In C, everything is always 100% of the time passed by value. Now, what does that actually mean? When you have the parameters for a function, what these really are is they are the definition of local variables. So if I define a function here, something like this, we'll just do a prototype. What I'm doing is I'm saying that this function test is going to have 3 local variables, an integer called x, a character pointer called y, and a size t, which is a long int, long unsigned, called h. Whenever I call a function, what happens is we take the argument. So if we take a look at this increment call here, increment has one formal parameter, or one parameter, an integer. What's going to happen is the value of the argument, so my argument is x, the value of that argument is 5, that value is going to be copied into the corresponding local variable. So you can imagine, if you will, when I make this call, there's sort of a hidden assignment at the top saying x is equal to 5, like this. Does that make sense? We don't see it, the programming language does it, but it's there. Now, when we are passing arguments into functions in C, it follows a particular calling convention, which is, roughly speaking, the first couple of variables are passed directly in CPU registers, the rest of them are passed via memory. For our purposes, though, we aren't going to worry about that, and we're just going to stick all of these variables directly into the stack frame. Know that in reality, some of them might not actually exist in the stack frame. That's one thing that it really isn't that relevant, but it is something to be aware of as I'm making a simplification. Okay, so let's take a look at what the stack frames for these two functions look like at the moment whenever we call the increment function. So we call increment and we are inside the function, but we have not yet actually done the x++ bit. And so here's what we have. We've got two stack frames. From the last video, I have fixed the ordering of the addresses, so they do go high to low now, as they should. And you will note that we have in main a variable x. It's an integer type, so it takes up 4 addresses, 4 bytes, and it has 5. Of course, it would be in a binary representation, but it has 5 stored inside of it. Now over here in increment, we have another set of addresses corresponding to that formal parameter, x. And you'll notice, of course, that two different stack frames, the addresses are different. So what happens is when I call increment, this 5 gets copied from this chunk of memory over to this chunk of memory. So we're looking at two separate x's. It's the same name, different corresponding memory address, which is fine because of C scoping rules, right? Every function has its own internal scope. Local variables are local to the function, so you can use the same names in multiple functions, no problem. As long as you don't duplicate names within the same function, you're good. So that's what we're seeing here. When I actually go to do an increment, what this does is it goes to this variable, finds the object associated, the 5, for example, and increases it by 1. So as you would expect, it's going to take this 5 and increase it by 1 to make it into a 6. However, because this is a local copy of the 5 that we're working with out here in main, and not, say, a reference to it or something like that, when the update is performed, it's performed on the local copy, and that new value is never propagated back, which means we get what we see. Inside of the function, the value has updated from 5 to 6. When the function returns, that update is lost, and the main's local x remains 5. So how can we fix this using pointers? Well, what we want is not for the increment function to see the value that we are incrementing. We want it to actually get some way that it can update this value out here. What if, rather than giving it the number that we wanted directly, what if we gave it the address of the number by using a pointer? This way, we can apply the increment operation based on memory address, not based on value, and that will allow us to update data outside of the direct scope of the function. So what would that look like? Well, that is written here in increment 2, and it looks pretty similar, but there's a couple of important differences. So first, you will note that the parameter that we are looking at is no longer int x, it is now int star x, which is to say that we are working with a pointer. So this is going to receive a memory address as an argument. When we actually perform the increment, what we're going to do is we are going to first say star x, we are going to dereference x, and then we are going to increment that. So what this dereference operation says to do is it says, go to the memory address contained within my variable, get me the thing that's there, and then increment that. Note the parentheses here are very important because the operator precedence on this is a little bit weird. I'll talk about that in a minute. And then likewise here when we print it, we don't just print x, we actually want to dereference it. We want to print star x because we want the number and not the address. The other difference is that when we call our function, rather than giving it x, rather than giving it the number 5, we're giving it the address of x. So what does that look like in terms of our stack frames? Well, here is the new situation. Main looks identical, that hasn't changed. However, when looking at increment, you will see that there are a couple of differences. First, you will note that x is a lot larger. It now refers to 8 addresses rather than 4. The reason for this is because I'm running a 64-bit machine, and pointers need to be large enough to represent any address in the address space. So on a 64-bit machine, you will get 64-bit pointers. So my pointer is effectively long rather than an int. And you will also note the value here is not 5, but is 10D, which is the address of the 5. Now what this allows us to do is when I do the increment operation here, it's going to say star x, which means get me this 5, and then increment that 5. So that allows my increment function, because it knows where the number is, to reach outside of its own local memory into the caller and update the value of the variable there. That's how this is working. Now to see this in action and verify that it actually works, go ahead and compile it. And as you can see, this version does in fact do what we want. The increment function makes it 6, and then it remains 6 inside of main. Now, as I had mentioned before, there is one thing you need to be aware of, which is that operator precedence will bite you if you're not careful. So let's go ahead and do this instead. Now you'll note that I'm getting a warning, which is usually a good idea to pay attention to those, but I'm going to ignore them because I want this to break. And let's see what happens when I do this without the parentheses. That's a little bit weird. So not only did 5 not change, but the print inside of the function gave me some random big number. What's going on here? Well, remember that a pointer is just an integer. And so it is perfectly valid to do arithmetic on pointers. That's called pointer arithmetic, and that's going to be an important subject in a later part of this series. So what we're doing here is we're actually incrementing the pointer and then getting the value that's there, rather than getting the value and then incrementing it. We're doing things in the wrong order. So just to be a little bit more clear about what's going on here, let me change this around. So I'm going to make this print out the address of x down here in main. And then up here, I'm going to print out just x. And we'll get rid of that to make the warning go away. So what I've done now is I've switched it from showing me the value of the integer to actually showing me the value of the pointer. So these are the memory addresses that we're working with. And note, they're going to look nothing like these because remember, stack is in the high address space, so these are going to be very large numbers. But if I go ahead and recompile with this update in place and run it, see what happens is we have in main, our x thing is 94, some junk and then 94. When I increment it, it goes up to 98 because I incremented the pointer. So I've changed the memory address. And then of course back in main, we're still 94. And that should make sense too, because I've just done with the memory address exactly the same thing that I was doing with the integer up here, right? I've changed the local value of my memory address, but that's not going to affect anything in main because that variable itself is strictly local to increment. However, when I dereference that memory address, it's now a new memory address, so it's not pointing to 5 anymore. It's pointing to whatever is after 5. To further illustrate what's going on here, let's take a look at some stack diagrams. This represents the situation of incrementing x without the parentheses. So just like we saw before, same basic setup, 5 is stored in x in main, and then x in our increment function is storing the address of that 5, so 10D. However, when we increment x here, because there are no parentheses, what we actually do is we increment the value of the pointer. So we're adding 4 to it. So that pointer is now no longer referring to 10D, but actually referring up here to 111. You'll note that this increment actually increased the value of the pointer by 4 and not by 1. Pointer arithmetic is a little bit weird in this regard. Later when we talk about pointer arithmetic, I'll explain why precisely that is and how it all works, but you may have a vague idea of what's going on by noting that x is a pointer to an integer, and an integer is size 4, and we just incremented it and it went up by size 4. So that's something worth thinking about. But that's what happens here. And of course, just like we saw with our very first example, incrementing the pointer doesn't affect anything going on in main. It is strictly restricted to changing things going on inside of our increment function. And so the result, it has no effect on anything in main. All right. Now, I do want to end with something for you to think about, and we're going to open next time answering this question. So I have here another example of working with pointers in the stack, and you'll of course note we have a warning indicating that something's probably hokey. So what we're doing here is I'm creating inside of this function a local variable y and assigning 5 to it, and then I'm returning the address of that variable. So I'm returning a pointer to this 5. So in my main function, what I do is I call the create function and store the address of this 5 inside of a pointer variable called x, and then I attempt to print the value. So we should expect to see 5. So I'm dereferencing x, which should take us back to there, and we should be good to go. Now, I'm going to go ahead and compile this. And again, we see that warning. And run it, and you will see we do not see 5. We, in fact, have an error. Depending upon your compiler settings, if you try this yourself, you may get some garbage value, or you may actually see the 5. But in more modern compilers, there's protections against this particular problem, which results in just a memory fault. So think a little bit about why this is happening. And actually, while I'm here, let me just show you this quickly because it will be very useful later. You may be used to, in higher level programming languages like Python or Java, when you encounter an error like this, seeing a stack trace, which is very helpful for figuring out where the thing broke. Obviously, when the C program breaks, you have no idea where it broke. It just says it broke. So if you want the stack trace, it's not that hard to get, actually. What you should do is you have to compile and add the G flag, which is going to enable what are called debug symbols. And now, rather than running the program directly, what you should do is use the debugger to run the program. So the debugger for GCC is gdb, the GNU debugger. So run gdb on a.out, which is going to drop you in the debugger itself. To actually run the program, just type R for run and hit enter. And it will run, and it will tell you precisely where the segmentation fault occurred, what line through the segmentation fault. While you're here, you can check the value of the variable, the value of the pointer that threw the fault, by using p and then the name of the variable. And if you want the stack trace, bt will give that to you. Of course, we only have one function in our stack, but if there were more, we'd see the full stack. So that, just real quick, that will be very helpful to you as you're debugging things as we move forward. You can use GDB to figure out exactly where the problem occurred. Or that might be a bad way of putting it. Not necessarily where the bug is, but at the very least where the error was thrown. In this case, the bug isn't, depending on how you look at it, isn't this print statement. It's something else. And then Q for quit, of course. Okay, so I will leave you with that question to ponder as to what the problem is. It might help if you draw some of these diagrams yourself and see if you can figure out what's going on. It may actually even be helpful to go all the way back to this sort of a view to get an idea for what's going on. Next time, we will address this question in particular and then take a look at how to fix it, which is going to lead to us expanding our map just a little bit into this red area down here. So, as always, I hope that you found this interesting and helpful, and I will see you in the next video.